So this is going to be our second lesson for the unit on forces and fields, and I want to do this one asynchronously. And so you're going to watch this one on some sort of personal device that's Wi-Fi capable. The goal, again, I just want to remind you what our goal is about doing it this way. We can learn a lot of things online nowadays. I've learned how to change the headlights in my car to learning how to work on my own sprinkler systems. So I think there's a lot of value in being able to be able to just find a video with information and watch that. And I could teach this lesson, obviously, to the whole group, but there's some real advantages to doing this asynchronously at your own pace. The first is that if I go too fast, you can slow down. You can pause the video. You can rewind it. Another interesting one is that you can actually speed it up. If you know how to go to the YouTube site, you can actually find a setting that allows you to speed this up to 1.5 times the speed. And so if I'm rambling on, like I kind of am right now, and you kind of want to go a little faster, you can. And that's one thing that you can't do in a traditional lecture. When there's a one-size-fits-all lesson that happens to all 20 or 30, or if you're in university, 100 or 200 person class, you go at the rate that the one person wants to go at. But we know that different individuals, they need different pacings. And so that's the beauty, is you can go at your own speed right now. And the other nice thing is that I should still be in the room right now. I want you to still ask me questions. A lot of times students are hesitant to ask questions when there's like a big lesson being delivered, because they don't want to slow down the group, or maybe they're a little bit fearful of asking and everybody going, well, that was a dumb question. Well, now you don't have to be quite as worried about that, because you're not stopping anybody, and everyone's kind of watching the video on their own. And so if you want to ask for help, go for it. I want to encourage that. Ask for clarifications. Pause the video. Call me over and say, Chris, how did you do this? Or, hey, what about this? I have a really cool idea. So anyways, without further ado, let's get into our video here, and let's discuss the concept of Coulomb's law for a second here. Okay, so Coulomb's law. We've been learning so far in this unit about forces, things that we've described, for lack of a better word, as, and hopefully we've heard this before, the term is called action at a distance. And the idea behind action at a distance is that we recognize that there's some sort of force occurring, and but we're trying to understand why. Why are these things that are not touching each other, hence the concept at a distance, why do these things cause actions? And I've got written down on this slide that physicists, we've known about laws of charges since ancient Greece. They've known that charged objects existed, and they've known about the two main concepts, the idea that there are unlike charges, which we now know as positive and negative, right? The negative and positive charges right here. We now know they're negative and positive. But there's also like charges, where you could have negative with negative, or possibly positive with positive. And we understand their interactions. Enough experimentation has allowed us to understand how they're going to interact. So if they're oppositely charged, they come towards each other. And if they're negatively charged, they oppose each other, right? So scientists have known about this for millennium, basically, in terms of this concept. They've known the idea of action at a distance. But as you can see in this bolded word I have right here, they didn't have a way of quantifying things. I mean, keep in mind, they didn't have access to, hundreds of years of internal understanding of how atoms work. We're actually going to focus on that later in this course. We're going to talk about people like John Dalton, Thomson, maybe you'll know some of these names already, Rutherford, and Bohr. But scientists, they didn't know about all of their contributions to understanding the internal mechanisms of atoms. They didn't even know about electrons yet, or protons. All they knew is that there were positive and negative charges, but they didn't know what they were. From a chemistry point of view, they understood that charges existed. They knew that, like, say, copper was positively charged and fluorine was negatively charged, but they didn't actually know that it was positive versus negative necessarily. They just knew they had opposite charges, and so therefore opposite charged things attracted and made compounds like, say, copper-2 fluoride. Right? So anyways, here's my goal. I'm getting a little off topic here. Is that the goal was then to try to quantify, well, how do these things attract, right? We recognize that sodium and chlorine have a tendency to want to join to each other. Again, we didn't know what was positive and what was negative yet, because these guys up here hadn't done experiments yet in order to prove that, but they did know these two observations. So I'm just pointing these two out right now. They understood that the greater the charge, the more attraction or repulsion there was. So if you had something that had the +2 charge, which again, keep in mind, they didn't know that it was positive versus negative yet. They didn't really understand that mechanism, but if they knew they had a +2 charge versus a +1 charge, like if you know your chemistry, copper's 2+, right here, and sodium is 1+. They understood that the 2+ was going to do more, right? It had more ability to have this action at a distance. Whereas the other thing they recognized is that the distances between charges, the more distance there was, the less the repulsion. And so this is actually really similar to around the same time frame, the idea of gravitational force. And so scientists began to recognize that electrostatic forces and gravitational forces were similar, because really they both worked under this premise of action at a distance, where two objects that were not directly touching each other could cause things to occur. Now, electrostatic forces are a little different. They can have both repel and attract, whereas gravitational forces, they really only truly attract. So what I want to do is remind you guys of an experiment you should have learned about back in Physics 20, and it was known as the Cavendish experiment. And I want to revisit what the Cavendish experiment did. Effectively, how it worked is that Henry Cavendish, he set up a wire, and this wire had the ability to torque or bend or rotate. And the way in which it rotated was based on there being like a fixed mass that was sitting, like, say right here. And I'm just drawing this mass and this mass on like a box to kind of illustrate the idea that it was fixed in place. These ones didn't move. But these other two masses, this one here and this one here, I'll label them as, for now, M1 and M2. These two masses, they did have the ability to move. And they were able to rotate this wire based on the distance, which we either use D or sometimes we use R for radius. Sometimes those are variables we use, based on the radius or distance between the objects. And what basically Henry Cavendish did is he was able to then figure out how much torque this wire was able to bend as these objects. Now, this is actually a picture of Coulomb's experiment, because gravity would only have caused attraction. So I know this picture shows this thing rotating in a kind of a counterclockwise direction, but it actually would have caused this one to go this way and this one to go this way. Anyways, hopefully you're familiar with this concept. Cavendish then measured the torque and then knew how much force of gravity there was, and his whole goal was to work on this formula here. We call this the universal gravitation formula, where he was able to then calculate this value here, capital G, which is the universal gravitational constant. Now, one of the things that maybe you didn't learn about when you were taught this in Physics 20 is that Cavendish experiment was a total ripoff of Charles Coulomb, who did the exact same experiment with the torsion balance, but he did it with charges. So Cavendish was actually a bit of a plagiarizer, honestly. He stole the idea of how to calculate the G value for gravitation from Cavendish. Now would be a great time to point out, if you're not familiar with the whole Cavendish story and how that experiment worked, now would be a great time to pause the video and ask me to give you a little rundown on it. But I want to describe what Charles Coulomb was doing, which then, like I said, Cavendish actually stole. So Coulomb's idea, same concept. What he did is he had a wire, and he had pre-measured how much force it took to basically torque this thing at a certain angle. And he had a pre-made chart. So he knew that if it required 1 Newton of force, it might move at, say, 2 degrees. But if you used 2 newtons of force, it could torque this thing 4 degrees. And 3 newtons of force would torque it 6 degrees. Something like that. He made himself a chart so that he knew, based on the angle of how much torque there was, he knew how much force there was. Then he also knew how much charge each of these objects had. Now, I actually screwed this up the first time. Really, the two objects should not be considered this one as 1 and this one as 2. That's actually kind of incorrect as to how this would work. Really, the 1 and 2 labels should be, let's go back to this. This first one here is 1, and then this one here is 2. And he set them up in this particular diagram so that they were like charges. So let's make this one negatively charged, this one be negatively charged. Because what's going to happen is, since number 2 is stationary, it has no ability to move. but object 1 does have the ability to move, and so it's going to start torquing this way. And really, this would have been object 1, this would have been object 2, both negatively charged as well, perhaps. Maybe he even made them positively charged, but I bet you he kept it all negatively charged. And what should happen then is this thing's going to want to rotate. Right? Then he measured the distance or radius between these two charges, and he quantified the charges. And if I haven't mentioned this before at some point, the quantity we use for charge is the letter Q. And so he knew how much charge there was on each one of these, and he was actually able to make a formula. And this is the formula ultimately that we're getting to, which is, well, I guess I'm not getting to it yet. I've got one more picture that kind of shows the exact same thing. You guys can read the words on here if you like, and it kind of describes how it works, but hopefully, here's the slide, there it is, with our formula. And what I want you to notice is this formula is very, very similar to the universal gravitation formula. I'm sure I have it on a future slide, but the universal gravitation formula is equal to a constant multiplied by two masses, the product of two masses, all over the distance between them squared. And this is what Coulomb actually discovered 10 years earlier. Cavendish was plagiarizing him, or at least he was borrowing his ideas. I don't think it's really plagiarism, but it wasn't an original idea. Now, the whole point behind this experiment was to isolate for a constant. And this constant right here, I have it written down, but it is 8.99 times 10 to the 9. That's this constant that Coulomb discovered. And we name it after him. We name it Coulomb's constant due to him. And so what it means is that if you know the force of attraction or repulsion, and we often use the subscript E next to it, this is going to be the electrostatic of attraction or repulsion. It's based on the two charges, the distance between them, and the constant. And one thing I need to point out then is based on one of our first slides that they already knew a relationship between things. If I were to ask you for a graph of force compared to, say, the mass of the object, they knew that if you increase the mass of the object, there was a linear relationship between the masses of the objects and how much force there was. Well, that was gravitationally. But the same logic applies if we're talking electrostatically. It's not about mass, it's about charge. If you have more charge, which we use Q for, you have more force. The other relationship they understood was that the force had a relationship with the radius squared that was actually a reciprocal relationship. And so your radius actually, the more your radius was, the less force you happen to have. And you can kind of see that in how the formula is devised. I'm just going to write it out here. F equals K Q over R squared. If you up the amount of charge, it would up the amount of force. But if you upped the amount of R squared, it would actually, like if you make the bottom of a fraction bigger, it would actually decrease the amount of force. And so these are your classic direct and reciprocal relationships. And so I want to discuss that a little bit on this slide here, the idea that this is similar to Coulomb's law, that there actually seems to be a lot of similarities between gravitational forces and electric forces. And I've got two notes I want to make out here. Pardon me. They're actually related to the to the constants is the first one here. The first is talking about the gravitational constant being so much lower. You'll notice gravitation's constant goes to the minus 11, whereas Coulomb's constant goes to the positive 9. And the question is, well, why is Coulomb's constant so much greater than the gravitational constant? And the reason why is that electrostatic forces are way stronger than gravitational forces, which actually seems counterintuitive to people at first, because we notice gravity a lot. On a macro scale, we recognize gravity as what keeps us stuck to Earth, and objects obviously fall due to gravity. But the only reason why we notice that gravitational attraction is because the mass of the Earth is just so massive. This second m often that's used, the mass of the Earth, because Earth is so huge, we notice gravitational attraction. But like, do you notice the gravitational attraction between you and your cell phone you're watching this on? Or between the pencil and the paper you're using? Well, those are very small objects, and there really is no gravitational attraction. There just is not that much gravitational attraction because those objects are quite small. However, we can actually do a lot of experimentation with small amounts of charge, very, very limited amount of charge. And there's actually a considerable amount of force. I mean, even if you've just ever taken your clothes out of the dryer and noticed some static electricity as you pull them apart, that cling that keeps them together, that you don't need a whole lot in order to actually have some attraction. So that's my first note right here, is that electrostatic forces are actually way stronger proportionally than gravity is. We just notice gravity more because the Earth is big. If we had a charge as big as the Earth was, I mean, there would be such an electrostatic force. I don't think we'd be able to even handle something that big. Okay, the second thing I need you to note is that gravity, I think I've ever mentioned this, gravity is only ever attraction, but electrostatic is attraction/repulsion. One of the things that I'm going to definitely assess you with, and there's a good chance the diploma will as well, is you need to be able to work with Venn diagrams. And so you need to know some similarities between gravitational and, let's use G for that. Actually, I'll use capital G, I think that'll work. And K for Coulomb for this, as describing the force of gravity versus the force of electric. And you should know some things that are in the similar spots, as well as the ones that are not. And so one of the differences between them is that although they both have the ability to attract, electric forces also have the repel ability. So, now, one of the things I want to point out before we keep working is that I don't want you to get stuck on positives and negatives. A lot of students do this. And if I've taught you before in Physics 20, I often like to tell you, don't get stuck on using gravity always as negative 9.81. I want to explain to you that you need to use your own logic to figure out whether to make something positive versus negative. Oftentimes we'll even see absolute values. If you've seen absolute value symbols before, we often see them in physics formulas because we really don't want to consider the positive negativeness of a value until after we're done. And that really applies here. Don't worry about whether you have positive and positive, positive and negative, or negative and negative. Don't worry about the types you have. Do the math, and then when you're done, figure out whether it's attracted or repelled. Attracted or repelled. Figure it out when you're done. So don't worry about trying to put positives and negatives into this equation. You use that concept later. Okay, now before we get to doing some math examples on this, which is kind of the reason why we're doing this video asynchronously, is because there's going to be some calculations involved. I need to explain the unit that we use for charges. And the letter that we often use for charge is the letter Q, little q, or capital Q. Both are considered to be a decent letter to use for charge. And the unit is something called a Coulomb, named after Charles Coulomb, obviously. And the idea basically is that a Coulomb is a group of electrons. It's a whole bunch of them. Because really counting an electron one at a time is kind of ridiculous. Let's say you have a whole bunch of electrons. You don't want to count out that you have 4,392 and just keep counting them out. We want to count them in like groups, kind of like how a dozen is used. And so in your data booklet, you're going to notice that there is a unit here. It's called an elementary charge, and it's given the symbol E. And what an E refers to would be like, say, 1 electron or 1 proton. Now, since protons and electrons, we now know, they didn't know it at the time, but since we now know that electrons are negative and protons are positive, all they knew is that they had the same charge. And so they've designated this as being the charge. And we've just stuck with E as being the letter for it. Now, E is actually for the word elementary charge, which is basically the smallest charge you can make. Because you can have something that's like, say, +1 or +2 or +3 or -1 or -2 or -3. So the E stands for the lowest amount of charge that's physically possible, because you can't have half of an electron, right? Now, again, at the time, they didn't know what electrons and protons were, but what they did understand was that they were equal to each other in terms of the value, and they eventually discovered what that value was. So the smallest charge you can ever have is this amount, because you can't have half of a subatomic particle. Kind of. We're going to learn about that actually later. You can actually have parts of subatomic particles, but for right now, let's assume that an electron and a proton is as small as things get. So here's another way of thinking of a Coulomb. This is how many electrons a Coulomb is. And if you're wondering how to calculate that, take the reciprocal of this number right here, like go 1 divided by this, or take it to the -1 power, and that will tell you how many electrons a Coulomb has, which, if you can get the scope of reference here, that's a lot of electrons. Oh, and so this is just the grouping we decided to go with. It's kind of a standard unit of measurement. It's kind of like, why did you pick 12 for a dozen? I don't know. Why did we pick 7 days in a week? There's really no logic to it other than now that we've chosen it, we got to stick with it. So I do have one more note down here as well. Most objects actually have way more electrons than this. Even though this number right here to the power of 18 seems like a lot of electrons, most objects have way more electrons than this. These are just the excess electrons. I want to write that word down here. When we're measuring charge, we're considering how much excess charge there is, because there could be 1 billion electrons and 1,000,000,001 protons, and we would then say that there's one extra elementary charge. It would just be a positive version. Right? If there was 1 billion electrons and 1,000,001 protons, we would say that there is one elementary charge. We don't actually usually put the positive or negative next to it. We just say that there's one extra charge, which is either in excess of protons or electrons. So keep in mind that this is not the total. Okay, so let's do an example. And that's kind of the reason why we're doing this lesson asynchronously, is that for some of you, now that I've given you kind of the verbal rundown on how the theory behind this works, now it's time to do some math on it. Before I forget, one more theory thing. On our data sheet, there are major physics principles you need to be aware of. For example, I believe 0 is uniform motion, and 1 is non-uniform motion. And like 4 is like conservation of energy maybe, and 5 is conservation of momentum. Okay, well, one of the formulas down below there, I believe, is conservation of charge. And that will be an overlying principle. I don't know whether it's number 6 or not. I don't have a sheet in front of me, but take a look at yours. And just be aware that conservation of charge is one of those big physics principles that needs to exist. Maybe I should go back a slide here before I move on. The idea that we're going to have excess electrons or protons, but it's not because we created them, it's because we moved them somehow. We either took electrons away or added protons somehow. Usually it's that we move electrons. We don't usually add protons, but that is actually possible. But yeah, conservation of charge just means that, like, you can't really make more protons and electrons. You can just make it so that the balance between them is different. So I think I should point that out before I do this example, is that the concept of conservation of charge, that concept there, is an overarching big picture principle we need to know. And I don't know if it's number 6 or not, but I know it's one of them there. So, okay, now let's do this example here. This one's pretty basic, the first one. We are going to have an object with a charge of -2 microcoulombs. So this is minus 2.0 microcoulombs. And so this is a negatively charged object. And it has been measured to be 0.15 meters away from a positively charged object with 3.0 microcoulombs. And we're being asked to figure out how much force is between them. Now, gravity would actually want to make these things be attracted to each other. But gravity is probably not going to affect many objects that are like 15 centimeters apart, that are relatively small, but I bet you there's some electrostatic force. And so this is about as straightforward as this formula comes. The formula is Fe equals K, Q1, Q2 over R squared. And we're being asked to solve for the Fe, so it's ready to go. Let's plug in some numbers. K is a constant. It is always 8.99 times 10 to the 9. Q1 is going to be 2 times 10 to the minus 6, because that is what a microcoulomb is. If you need a little tutorial, maybe pause the video and have me explain, but U is the symbol micro, and it is a times 10 to the minus 6. There's actually a whole chart of them on your data table, if you aren't familiar with that, for things like micro and mega and tera and exo and milli and centa, all those things. So, now, you'll notice I didn't put the negative sign in here because it really doesn't matter whether it's positive or negative when I solve this thing. I'm going to finish off the rest of this and then I'll explain why. Do not forget to square the denominator, by the way. Common mistake students make. They forget to square the denominator. So I'm going to try the math here. You guys can follow along. One of the points of doing this asynchronously is this should give you time in order to see that I'm doing the work properly. Like if you want to double check calculations, You should do this now. Sometimes I make mistakes, so hopefully I won't make an error. But I calculated this value. It took me a second. I got 2.397 or so. And that would be in newtons, because that's what forces are measured in. And so that's a 3, by the way, right here. So double check in your calculator, make sure I did it right. And if you have any issues, call me over. I'll try to help. But now I want to explain something here. Forces are vectors. We need to give a direction. And so if we need to know the electrostatic force between the two options, that force is like together, as opposed to repelling. These two objects want to come closer and closer to each other. And so the negative object is being pulled this way, and the positive object is being pulled this way. And so that's really important to notice, is that I didn't need to worry about the positive or negative. I know that we could have put a negative in front of this number here, but it really doesn't matter, because the raw value is all that matters here. I then need to use my logic and figure out whether it's together or apart. We should do sig digs, though. So let's say that these things are coming together at 2.4 newtons. I'll just put an arrow there for together. Now I need to point something out. According to Newton's third law, for every action there's an equal and opposite reaction. This object is being pulled with an electrostatic force, and so is this one. They're both being pulled via the same force, and it's not half as much. It's not like they each get half the amount of force. They're each being pulled with the same force, because the only reason why the force exists is because they're both pulling on each other. And so if it ever comes up, don't divide that force by 2. That would be very wrong. Okay? The amount of force they're experiencing is the same for both. Now, it's actually possible and very likely that you're going to be asked to take information like this and then make that force that you just solved for equivalent to other things, like, say, mass times acceleration, or maybe mv squared over r, which is centripetal motion. Or maybe it'll become equivalent to another force like gravity, or equivalent to a force that we haven't even gotten to, like a magnetic force. It's very likely that you're going to be asked questions where you actually do multiple steps. You're not likely to get a question where they just give you this information and say, solve for this. That's way too easy. It happens once in a while, but that's pretty rare. So just be aware that we're probably going to take this to more locations, especially this first one. This is Newton's second law. And so it's very likely that you'll be asked to combine that with Newton's second law and then say solve for an acceleration. And then once you solve for an acceleration, maybe you'll solve for something else. So, okay, hopefully that made sense. Pause, rewind. Otherwise, I'm going to try another example. And that's what I love about doing it this way, is I can cut down all the wait time. So let's move on here. We got two charges. We're actually given the force. Now we're being asked how far apart they are. And so really, this is that same formula. Your electrostatic force is K times Q1, Q2 over R squared. But we're being asked to find the distance. So I'm going to rearrange this. I always like to rearrange first. I find that to be most valuable. And I'm going to rearrange my formula to this. The radius will be K Q1, Q2 over the force, and then square root to get R by itself. And if I lost you there, if you couldn't follow that algebra, just kind of doing that in your head, can you pause the video, call me over, I'll try to help. But this is pretty straightforward. This is just a one-step kind of question. K is 899 times 10 to the 9. Q1 is going to be the 1.8 times 10 to the minus 6. Q2 is the 2.4 times 10 to the minus 6. And we were given a force, which was 2.2 times 10 to the minus 3. So it's about as straightforward as you can get. Again, while I'm doing the math here, I just want to point out that it's very rare that you're going to be given a question on Physics 30 where you only do one step. Okay. Now, sometimes when we're learning this, I will give you a question that really only has one step, just to kind of build some skills. But we're not going to do much of that, because that's just not a difficult enough level. We need to move past that, and we need to move past that quickly into more problem-solving areas. So I'm going to solve for this distance, and I got a distance of 4.2 meters with sig digs. And because of this, we're actually finished the question. Now we know the distance, but like I said, it's more than likely that you're going to be asked to then take that distance and do something else with it, right? Using it in a subsequent calculation. But if you're able to follow that, again, I'm going to move on to the next example, because I love that I can just breeze through these so much quicker now, since I don't have to do wait time. So here's another example. We want to find the net force. And so whenever we have a net force, what we want to consider is that the two objects that we're not considering, like this one right here, we want to pretend that this one is stationary, like it's on like a box. And this one is also stationary, like it's on a box. But this one up here, the negative one, imagine it's hanging from the roof. And it has the ability to either get pulled towards the positive or towards the negative. And we want to kind of figure out which one is going to win this particular fight. And if I were to ask you which major physics principle we're using principle number 1, non-uniform motion. And the reason why we're using non-uniform motion is that the net force does not look like it's going to be 0. It looks like someone is going to win this competition for the blue object, and it's going to swing either to the left or to the right. And so ultimately what we're going to need to do is figure out the electrostatic force that's going to cause it to get pulled this way, find the electrostatic force that's going to cause it to get pulled this way, and since one of these vectors is going to be bigger than the other, we'll know. And I think I can even make a prediction before we start. If you haven't done the math kind of in your head here, the distance is equal distance. Like if this is 330 all across and that's 165, this is also 165 centimeters from here to here, which means they have the same distance. So really the only manipulated variable that matters otherwise is the fact that this one has a smaller charge than this one. So if the one over here on the far right has a higher charge, it will then have a higher force. And if I were drawing a vector free body diagram here, this would be it. My negative charge is getting pulled more towards the right than to the left. So like I said, all we got to do is just find two forces and subtract them. So I'm going to do the work for that, and we'll calculate the value. Let's find the first force of attraction. Let's go with 8.99 times 10 to the 9 times by 2.10 times 10 to the minus 6 times by 1.00 times 10 to the minus 6, all divided by the distance, which was 1.65 centimeters. And the way I'm going to convert that is by making it to the minus 2, because I know that minus 2 is a centimeter. Now, that's one of my shortcuts that I use. If you'd like to convert this number into 0.0165 meters, you're welcome to. That works just as fine. But again, because this is a YouTube video, I can kind of speed things up a little bit, because I know that if you need to, you can pause, right? So pause if you need to, if I'm losing you and if I'm going too fast. If I'm not going too fast, hopefully I just won't make a math mistake right now, because that does happen. I'm just typing numbers in my calculator here. I calculated this value here, so hopefully some of you will check this as well. I got 69.34 newtons, and I'm going to store that in my calculator as letter A, because I know I need to use that again later. So store that as letter A. And now I'm going to redo the entire thing again, only now I'm going to do it for the second of the two forces. So the math is the exact same. And by the way, I should point out that you need to show at least this much work when you're doing your written response questions. I actually really skipped something. I really should have written out this formula first. Fe equals K Q1 Q2 over R squared, because on my written response rubric, if you haven't had me explain this to you before, you're expected to show a formula. So that's this step here, show a formula. You're expected to show substitutions, which is what I've done right here. After that, all I need is an answer. So you don't have to show all the little steps in between. Just give an answer. This is answer A. So I can speed up. I can go to the next one. This is 210 times 10 to the minus 6. The formula hasn't changed. This time it's a 1.50 times 10 to the minus 6. And again, the same distance is 1.65 times 10 to the minus 2 squared. And I just need to type this in my calculator. I can actually go back up and just change one number, I think. Make that 1.50, divide by 1.65 times 10 to the minus 2 squared. And this one gives me more force. I expected it to. I have 104.01 newtons, which I will save as letter B. Store as letter B. And like I said, then in my free body diagram, if I go back up here, this is B, this is A. B is bigger than A, so to find the net force, I'm going to take B and minus A. And that will be my net force. And so B minus A with sig digs, because I better do sig digs to finish it. Looks like I get 3 sig digs, so let's call this 34.7 7 newtons. And I should give a direction to it. The net force, I believe, was going towards our right. There we go, there's our answer. Now, like I said, it's unlikely that you're going to be asked to do just this. Chances are it's going to ask you for, like, say, what is the acceleration of the object? Which means, well, net force is equal to mass times acceleration. So if you had been given a mass, you could divide by both sides by mass, and then you could solve for an acceleration. It's very uncommon you only get one-step math problems in Physics 30. Often it is part of a much larger picture. But saying if it doesn't and you have questions, pause. That's the whole point. You get to go at your pace, not my pace. So I'm going to move on to our next example here. I think this is actually our last example. No, second last example. It's actually possible to do examples that are in 2 dimensions. And this is very similar to momentum, where we actually have to account for a y and x axis. And as we know, vectors have to be done in all dimensions. You have to do x and y simultaneously. I can't just find the amount of force that exists here and the force that exists here and just add them. I have to account for the fact that this one is a y dimension and this one is an x dimension. And so if I'm trying to consider the net force on Q2, again, keep in mind, the way we kind of consider it is that these ones here are stationary. This one here is stationary. They're not going to move. But this one right here, Q2, it's mobile. It has the ability to move. And if I were to draw a free body diagram, it has 2 forces acting on it. So Q2 is going to be repelled from Q1, right? Because they're both positive. So it's going to want to be pushed this way. And so why don't I call that F1? However, due to this other one over here, it's actually going to want to get pushed away from the green one, and so F3 is actually going to push it that way. Now, a common misperception kids have is they think, well, we need to solve for a hypotenuse like this, but that's not how this works, right? In a true vector triangle, although this is a free body diagram, let me undo that because I don't want to have wrong work on there. This would be a free body diagram, but in a vector diagram, you draw it like this. One force is going to push you this way. One force is going to push you this way. And the net is going to take you on a hypotenuse like this.